this lecture, we are going to draw the shear force, bending moment, and axial diagram for the frame shown in the figure. There are two horizontal members and two vertical members in this frame. So we are going to follow these steps to get our desired result, that is to draw shear force and bending moment diagram. So we are going to first determine the support reactions, then draw the free body diagram and determine internal force at each joint. Then we are going to write the shear force and bending moment equations for each member. We are going to determine functions v of x and m of x and use these functions to draw shear force and bending moment diagram. First step, determine support reactions. We are going to use conditions of equilibrium, summation of f of x, summation of f of y, and summation m equals 0 to find out the reactions at A and B point. So let's first name these reactions. At A point there is hinge, so there will be two reactions, one vertical and one horizontal. So let's name this as RAY and this one as RAX. And at roller we have only one vertical reaction. Let's name this reaction as RBY. Before applying conditions of equilibrium, we are going to convert these UDL into resultant point load. To calculate the value of this point load, we just have to calculate the area of this UDL. And the area of this UDL is equal to 12 multiplied by 9, which is coming out to be 108. And the area of this UDL is equal to 15 multiplied by this distance, which is 20. So 15 multiplied by 20 would give me 300. And for this point load, we have 15, which is the intensity of the loading at this 5 meter span length. So 15 multiplied by 5 is equal to 75 kilonewton. So let's apply the first condition of equilibrium, that is summation of force in x direction. And let's take rightward going force as positive. So how many forces are there which are acting in x direction? We have this RAX and this 108. So RAX is going to be negative since it acts opposite to my sign convention, and this 108 is going to be positive. If I simplify this, RAX is coming out to be equal to 108 kilonewton. Now let's apply second condition of equilibrium, summation of forces in y direction. And let's take upward force as positive. So RAY, how many vertical forces are acting in this frame? We have this RAY, RBY, this 375. So RAY is going to be positive plus RBY, and these two forces, 75 and 300, are going to be negative. So if I simplify this, I'm going to get RAY plus RBY is equal to 375. And let's name this equation as equation number 1. Now let's apply the last condition of equilibrium, that is summation of a moment about a particular point equals 0. And let's take this point. Let's sum of the moment about this point, A point, and take clockwise moment as positive. So we know that moment is force and distance. Let's try to find the perpendicular arm and distance for each force. So 108 with respect to A point has moment or has perpendicular arm of 4.5 meter, half of this span length. And this 300 has a perpendicular arm of 10 meter. And this 75 has a perpendicular arm. If we first calculate this distance, this is going to be 2.5. 2.5 plus 20 would give me 22.5. So 75 has a perpendicular arm of 22.5. So let's write this equation. So first we have 108, which is acting in clockwise direction and has a moment arm of 4.5 meter. And then we have this 300 force, which is also acting in clockwise direction. This is going to be positive as well. 300 into 10. And we have this 475, and it has a moment arm of 22.5. Okay, so there's one other force which is also creating moment about point A, and this is the reaction RBY, and this is creating counterclockwise moment about point A. So this is going to be negative with a moment arm of 20 meter. So if we solve this, if we simplify this, RBY is coming out to be equal to 258.675 kilonewton. And if I substitute the value of RBY into equation number 1, equation number 1 implies that RAY is equal to 375 minus 258.675, and if I calculate RAY from here, it's coming out to be equal to 116.325 kilonewton. And we are done with the support reactions. Now let's draw the free body diagram. Okay, the second step involves drawing the free body diagram of the frame and obtaining these internal forces at joint C and at joint D. So before calculating these internal forces at C and D, let's discuss sign convention. Let us assume that this is a structural element. If the moment is produced in such a way that it produces sagging in the beam, then this moment will be positive. For left hand side, clockwise moment will be positive, and for right hand side, anti-clockwise moment will be positive. If the shear force is produced in such a way that it produces a clockwise effect, rotation effect on the structural element, then this shear force will be positive. For left hand side, upward force will be positive, and for right hand side, downward shear force will be positive. For normal force, if it comes out of the section, then it's going to be positive. For left hand side, if it goes to the left, it's taken as positive. For right hand side, if it goes to the right, it's taken as positive. So if we solve something, let's say we want to determine the shear force and bending moment diagram in this beam. So if we go from left to right, we are going to use these sign conventions. We are going to take these sign conventions as positive. Clockwise moment positive, upward force, shear force is positive, and this leftward going normal force is positive. And if we are going from, if we want to solve this beam going from right to left, that is like this. So you'll take these sign conventions as positive. The idea is to get the same shear force bending moment diagram, whether you draw it from here or from here. Let's first determine shear force at this point. To calculate shear force, we are going to take the summation of all forces that are acting in y direction, that is this direction, and that are before this section at the left hand side. So we have two forces. We have this UDL which has a resultant point load of 108 and this 108 force. And we are going to use these sign conventions because we are going from left to right. Upward force will be positive. So V is equal to, this will be positive 108 since it's going upward, and this will be negative. And if you calculate it, it's coming out to be 0. Now to calculate moment, we just need to take the algebraic sum of the same forces with respect to this point. So moment is nothing but the algebraic sum. So there are two forces. This force which is acting in clockwise direction, and since clockwise moment is positive, then this will be positive, and it has a perpendicular arm of 9 meter. And this force is creating counterclockwise moment, hence it will be negative. And it has a perpendicular arm of 4.5 meter. If you solve it, it's coming out to be around 486 kilonewton meter. And this is acting, since it's positive, this is acting in clockwise direction. Now remember, we need to apply internal force here in such a way that this segment, this member is in equilibrium, should be in equilibrium. So we just need to multiply this with -1, and this will be 486 kilonewton meter. And this minus sign indicates that this is acting in counterclockwise direction. So we need to apply moment of 486 in counterclockwise direction. And for axial force, in order to keep this segment in equilibrium, we just need to apply 116.325 in downward direction. So this segment will be kept in equilibrium in this way. Okay, now we need to transfer these forces, these internal forces, to other end of the member, that is here. To do that, we are just going to write them, draw them here in opposite sense. If it's going downward, then it will go upward. If the moment is acting in clockwise direction, we need to apply here in counterclockwise direction. Here the force is going downward, I've made this force as going upward, and this moment is acting in counterclockwise direction. This moment will be in clockwise direction. So this force is going to be 116.325, same in magnitude but opposite in direction, and this force is acting in clockwise direction, 486. Okay, so why do we need to do that? So at joint, we need to keep the summation of moment and summation of force equal to 0. Moving forward, we need to calculate reactions here, internal reactions here. So for shear force, let's first set the local axis. I've taken this as x and this one as y. So for shear force, stand on section C on the left hand side, take the algebraic sum of all the forces acting in y direction. So this UDL, if you convert it into a point load, this will be around 15 multiplied by 20 would give me 300. So we have this vertical force which is acting in upward direction, and it matches my sign convention for left to right. So this will be positive 116.325, and this point load, resultant point load 300, will be negative. And if you solve this, it's coming out to be minus 0.675. The minus sign indicates that this force, this shear force, is acting in downward direction. So we just need to multiply it with -1 to keep this member in equilibrium. So the force that we need to apply to keep this member in equilibrium in case of shear is 183.675 going upward. Now let's try to calculate the moment at this section. To calculate moment, stand on the section C on the left hand side, take the algebraic sum of all the moments. So first we have this 486 which is acting in clockwise direction, and this is going to be positive. And let me write it here, the sign convention, moment will be positive if it's going clockwise. And we have this force 116.325 which is creating a clockwise movement. So this is also going to be positive 325 into 20, and this moment 300 has a perpendicular arm of 10 meter, and this is creating a counterclockwise moment, hence negative. 300 multiplied by 10, and if we solve this, minus 187.5. The minus sign indicates that it's acting in counterclockwise direction. So just multiply it with -1 because we need to apply it in opposite sense to keep the member in equilibrium. And since it's coming out to positive, we need to apply a clockwise moment. So let's apply clockwise moment here, and this has a value of around 187.5. If you have some overhanging part in the frame, just try to analyze it like a cantilever. So we have a cantilever here, and there's load of 15 kilonewton per meter acting on it, and it has a span length of 5 meter. So if you just calculate the reactions here, you will obtain the internal forces at this point. So 15 multiplied by 5 give me the resultant load for the point load, resultant point load, and it's coming out to be 75. And if I calculate this reaction, this will be 75. And the moment produced here, this moment, will be equal to 75 multiplied by 2.5, 187.5. So basically what I'm doing is I'm applying conditions of equilibrium, summation of f of x, summation of f of y, and summation of moment to get these reactions. Now just write them here. We have 75 kilonewton force, and we have this moment 187.5 acting in counterclockwise direction. Now we need to transfer these moments and shear force to this end of the member. To transfer the moment here, take the algebraic sum of the moment at this point as well as this point and reverse it. So this is acting in counterclockwise direction, this is acting in clockwise direction, this will be positive, and this is acting in counterclockwise direction, so this will be negative. So there will be zero moment transfer to this end of the member. Now let's do the same thing for the shear force. To transfer shear force here, we need to algebraically sum the shear force here and here. So both of them, since are going upward, this will be positive as well as 75 will be positive. So this is coming out to be 258.675, and since it's positive, it's acting upward. Now we need to multiply this with -1 in order to transfer it. So we need to apply 258.675 downward. After this calculation, what we are going to do is we are going to isolate each and every member and then write shear and moment functions for the members, and then we are going to plot the shear force, bending moment, and axial diagram for those members. So let's first take this member. Okay, first we are going to plot the shear force and bending moment diagram for member AC. To do that, we first need to cut a section, imaginary section, to write the moment equation and shear force equation. So let's take this coordinate as x, starting from here, and first let's set the local axis. Take this as y, going towards left, positive, and x going upward as positive. Okay, the sign convention. If you're solving something from left to right, upward shear force will be positive and clockwise moment will be positive. To write the shear force equation, stand on the section, see on the left hand side, take the algebraic sum of all the forces. So there are two forces. One is this UDL and one is this point load support reaction. This resultant point load will be equal to the area of this UDL before this section. So this is going to be equal to 12 into x. And since this 12 into x is going towards the right or in the negative y, this is going to be negative, and 108 is going upward. And since if you're solving from left to right, shear force is positive going upward, so 108 will be positive in this case. Stand on the section, see on the left hand side, take the algebraic sum of all the moments. So we have this force 12x creating moment counterclockwise moment, this will be negative, because according to our sign convention, clockwise moment is positive. So minus 12x, and it has a moment arm of x by 2. Since the whole distance is x, if we divide it by 2, we will get this half distance, plus this 108 is also creating moment about this section. So 108 is creating clockwise moment, hence positive, and it has a moment arm of x. Now if you simplify this, we get minus 6x square plus 108x, and this is our moment equation for this member. Okay, we are going to plot our shear force here, and moment diagram here, and axial diagram here for this member. So this line is basically the 0, 0 line. In order to plot this graph, we just need to insert certain values of x to obtain shear force and moment values at different points. So let's use a table. We will have x here, shear force here, and moment here. X is 0 here at A point, and it goes up till 9. So it's entirely up to you what difference do you take between the values of the x. So I've taken the difference, kept the difference as 3. So I want to obtain the values of shear force and moment at 0, 3, 6, 9. I'm going to substitute 0, 3, 6, 9 in this equation as well as in this equation. At 3 we have 72, at 6 we have 36, 9 we have 0. Similarly, substituting these values here and here, 0, 3, 6, 9, you will obtain different values of moment. At x equals 0 we have moment equal to 0, at 3 we have 270, at 6 we have 432, and at 9 we have 486. So let's now plot these values onto this graph. What is the highest value of shear force in this table? We have 108, so let's mark certain values on the axis, keeping the maximum value in mind, 150, and on this axis we have x values, and on this axis we have the shear force values. Now let's mark the x values on this axis. 3, 6, and 9 would be here. At x equals 0, what is the value of the shear force? 108. So 108 would be somewhere over here. At x equals 3, we have 72. 72 would be somewhere here. At x equals 6, we have 36, and it would be around somewhere here. And at 9, we have shear force equals to 0. To draw the shear force, just graph through the plotted points. And this is going to be positive. Similarly, plot the moment diagram. So the maximum value of moment goes up to 486. So let's mark the axes, keeping that value in our mind. Similarly, this would be 3, this would be 6, and this is 9. So at x equals 0, we have moment equals to 0. And at x equals 3, we have 270, which would be around somewhere here. And at x equals 6, we have 432. 432 will be somewhere here. And at x equals to 9, we have 486, which would be somewhere here. Okay, to draw the moment diagram, just graph through the plotted points. So this will be our moment diagram. Also observe that the maximum power of x in Shear equation is equal to 1. So this is a linear function. And in the case of moment equation, the maximum power of x is equal to 2, which tells us that this function is a quadratic function. So that's why you can see that you can observe here that the shear force is a linear function. It's represented by a straight line, where the moment diagram is made by a curved line or a quadratic line. So moving forward, now we are going to draw the axial diagram for this member. So in order to draw it, we need to look at the whole behavior of this member, whether it is being compressed or being elongated by the axial force. So in this case, the axial force is 116.325, and in this case it's compressing the member. So this would be negative. This would be a negative diagram, a negative rectangle, and the y value would be 116.325. On x-axis we have x values, and on y-axis we have the axial force. Now we are going to draw the diagram for the CD member, this one. So first we need to write the shear force and moment equation for this member, and here we know that at this point, after this point, the discontinuity in the loading occurs at D point. So we need to cut a section before it, and we are only going to require one section. And let's represent this coordinate as x. Now to write the shear force equation, just stand on the section, see on the left hand side, take the algebraic sum of all the forces. So we have this UDL acting in y direction, and this 116.325 acting in upward y direction. And if you are solving something from left to right, we discussed it earlier that shear force upward is taken as positive and clockwise moment is taken as positive. So 116.325 is going to be positive, and this UDL resultant point load is equal to 15x. This is going to be negative because this is going downward. Similarly, for moment equation, we stand on the section, see on the left hand side, take the algebraic sum of all the moments. So this 116.325 is producing clockwise moment about this section, so this is going to be positive, and it has a momentum of x meter. And similarly, this is a moment we don't need to calculate, we don't need to multiply it with a perpendicular arm. So this is acting in clockwise direction, this is going to be positive. And we have this 15x which is producing a counterclockwise moment about this section, so this is going to be negative, and it has a perpendicular arm of x by 2. So if we simplify this equation, we get, okay, now we are going to insert certain values of x to obtain different values of moment as well as shear. So we are going to use this table x, b and m. So x is equal to 0 at this point, and the last value of x is going to be here, and it's going to be equal to 20 meters. And in between the values of the x, I'm taking difference equal to 5. So the next value is going to be 5, 10 and 15. I'm going to insert these values of x, 0, 5, 10, 15 and 20 in this equation as well as in this equation, and I'm going to write those values over here. So after this, I'm going to draw my shear force here and moment diagram for this member here, and this would be x, and on this axis this would be the value of shear force. Similarly, the ordinate over here would be corresponding to the value of moment. So the highest value of shear force in this column is 183 minus 183.675. So keeping in mind that value, let's try to mark these axes. 100 would be here and 200 would be here, and this would be minus 100 and minus 200. And now let's mark these x values on the horizontal axis. So this would be 20, and half of it would be 10, and 5, 15. So at x equals to 0, shear force is 116.325. So 116.325 would be somewhere here. And at x equals to 5, it's equal to 41.325. So this means that it would be around somewhere here. Similarly, at 10, it's equal to minus 33.675. This would be somewhere here. And at 15, it's minus 108.675. This means that it would be here. And at 20, we have minus 183.675. Minus 120.675 will be somewhere here. And if you notice, the power of the x in the shear function is equal to 1, which means that it's a linear function and it would be represented by a straight line. So if I try to connect them, this should be a straight line. So this is going to be positive and this is going to be negative. And to find this value, you just need to equate this equation to 0. So v of x equals to 116.325 minus 15x equals 0. And if you calculate x from here, so this distance from here to here, where shear force is 0, is equal to 7.755. And the maximum value in the moment is equal to 899.25, and mark this axis, y-axis, according to this value. So let's say our 500 is here and our 1000 is somewhere here. And do we need to plot in negative? Yes. So our 500 is here. So at x equals 0, we have moment equals to 486, which would be somewhere over here. And at x equals to 5, we have a moment value of 820.125. Similarly, at 10, we have 899.25, which is pretty much close to this value, and this would be somewhere here. And at 15, we have 543.375. At 15, this is 15 here, we have 543 somewhere near here, and this point would be located here. And at 20, we have minus 187.5. So minus, negative, and this would be somewhere here. And we know that in moment equation, the highest power of x is equal to 2, which tells us that this function, the graph of the moment diagram, would be quadratic in nature. So this is not going to be a straight line. The slope of the line, the slope of the curve would be changing at every point. So if you connect these points together, we would obtain the moment diagram. So it would be positive here, and there will be some negative portion here. This is negative portion. Furthermore, this is not the maximum value. At 10, we have 899.25. This is not the maximum value of the curve. To find the maximum value of the curve, you need to insert x equal to 7.755 into this equation, because the maximum moment is located where the shear force is 0. So you need to insert 7.755 into this equation mx. So let's do that, and if I insert, it gives me 937.05. This is 937.05. So the maximum value is located somewhere here, and this is coming out to be 937. And we can see that in this member there is no axial force compressing or elongating this member on both ends. So the axial diagram will be a 0, 0 line for this member. This is the axial diagram. Using the same procedure and method, diagrams for DB and DE members have also been plotted.